In this section, we'll focus on why residual connections matter in transformers. They're a simple idea, but they're essential for training deep models reliably, preserving information, and helping gradients flow through many layers. If you're aiming for an LLM engineering role, this is one of those core concepts that connects architecture fundamentals to practical system design, and even comes up often in interviews. Here's our roadmap for the session. We'll start by defining residual connections and the basic math behind skip paths. Then, we'll look at why they matter, especially for optimization, information flow, and computational efficiency. After that, we'll compare normalization choices, focusing on post-layer norm versus pre-layer norm. Finally, we'll connect all of this to career applications, including project ideas, interview preparation, and portfolio building opportunities. Here's the core formula behind each transformer block. The incoming hidden state X goes through a sublayer, like attention, or the MLP, producing a learned update. Then, that update is added back to the original X through a residual connection. After that comes layer normalization. This isn't just a design detail. The model keeps every sublayer and embedding at the same dimension, so these residual additions work cleanly throughout the architecture. A useful way to think about transformers is not as isolated layers, but as one shared workspace flowing through the whole model. The residual stream. Each attention block reads from that stream and writes back an update. Then the MLP reads the updated stream and adds another increment. This residual stream view, emphasized in the Tracks paper, is central to modern mechanistic interpretability, activation engineering, and model editing. Reason 1 is optimization in deep networks. Training very deep transformer stacks is hard, because without residual connections, gradients weaken and convergence becomes unreliable as models scale. Residual paths solve that by preserving an identity route for information, while each block adds a bounded update instead of rewriting everything. That's what makes deep stacks trainable in practice, and it's a point supported by work like Transformer and rewiring transformers. Reason 2 is information preservation across depth. As networks get deeper, skip connections help keep earlier features available at every layer. Without those residual paths, the signal can gradually collapse. In pure attention models without skip connections, research shows the output can converge doubly exponentially toward a rank 1 matrix, which means most representational richness is lost. So with residuals, information stays accessible. Without them, deep representations become increasingly uniform. Reason 3 is that the residual stream isn't just bookkeeping. It's a meaningful object to analyze. Anthropic's work on privileged bases showed that, in large models, some residual stream coordinates become unusually strong outliers. That's important. If you inspect activations across layers, patch residual values, or compare layer contributions. In practice, mechanistic interpretability, activation engineering, and model editing all rely on treating the residual stream as a real computational workspace. Residual connections don't work in isolation. They're tightly linked to normalization, and that placement really affects training behavior. In the original post-LN design, layer norm comes after the residual addition, but that can lead to unstable gradients early on. In pre-LN, layer norm is applied before the sublayer, which makes optimization much more stable. That's why most modern LLMs use pre-LN. So in interviews, treat residuals and normalization as one joint design choice. This slide highlights how much innovation is still happening in the residual design space. Realformer adds residual attention, meaning each layer can reuse attention maps from earlier layers, and it shows strong gains over standard transformers across many tasks. Catformer pushes in a different direction, using concatenation instead of standard residual or gated paths. Together, they suggest that better models often come from rethinking how information flows through the network, not just changing attention itself. Here's one of those implementation details that really separates candidates. In the annotated transformer, dropout is applied to the sublayer output before it's added back through the residual connection and normalized, not after. You should be able to look at a transformer block in code, trace the residual path, identify whether normalization is pre or post layer, and explain why those choices affect stability, training behavior, and model performance. Here's a strong portfolio project. Implement both pre-LN and post-LN transformer blocks in PyTorch, train them on a small dataset, and compare how they behave. The key difference is where layer norm happens, before each sublayer in pre-LN, or after the residual addition in post-LN. In practice, pre-LN is the modern default because it usually trains more stably, while post-LN is useful for understanding the original transformer design. Here are 3 strong portfolio project ideas. First, build a residual stream probing notebook that logs hidden states across layers and shows how token representations change as attention and MLP blocks add updates. Second, run an ablation study by training a small language model with standard versus weakened residual connections. Then compare loss, gradient norms, and perplexity. Third, use track to trace how a simple algorithm is built step by step through residual updates. This slide maps common interview questions about residual connections. At the architecture level, the key idea is that residual paths preserve an identity root, so each layer makes bounded updates and training stays stable. As models get deeper, normalization placement matters, especially the difference between pre-LN and post-LN for gradient flow. For debugging, I'd inspect residual stream activations and gradient norms layer by layer. And for interpretability, the residual stream acts like a shared workspace across the model. The key interview answer is that residual connections matter because they give the model a stable path to carry information forward. That helps optimization by keeping gradients clean, preserves earlier representations instead of overriding them, and creates the shared residual stream that both attention and MLP layers update. In practice, I'd tie that directly to code I've written, experiments I've run, and the failure modes I've investigated in deep transformer stacks. The broader career takeaway is that residual connections touch almost every important layer of transformer work. Architecturally, they explain why the block is shaped the way it is. For optimization, they affect how normalization and training dynamics behave. For interpretability, the residual stream becomes a useful unit of analysis. And in implementation, understanding residuals helps you modify blocks and test ideas in practice. They're simple to explain, but deep enough to support serious technical work. Here are the key takeaways. Residual connections aren't just a helpful trick. They're built into the architecture and shape how information moves through the model. It's also worth getting comfortable with the residual stream framing, because that's the language used in mechanistic interpretability and a lot of modern LLM analysis. And finally, pay attention to normalization choices. Pre-LN versus post-LN changes stability and gradient flow. The best way to learn this is to build the block and test it yourself.